Now let's consider the case where we have selections when elements can be chosen more than once. And this is the case where you have a number of elements and you're grabbing these elements, you're selecting these elements, but some of them can be repeated. A good example would be one in the textbook on page 423. Suppose that 7 people in a hotel conference room call for refreshments from room service. And the refreshments are limited to 3 types: coffee, tea, or milk. And you will see here these uh, refreshments expressed as letters here. It's C for coffee, T for tea, and M for milk. And the question here is how many different selections of 7 refreshments, because there are 7 people, are possible. Uh, so for example, one different selection would be 3 coffees, 2 teas, and 2 milks. Now it's important to realize that uh, this selection and this selection here, they're the same. Yes, perhaps the first person chooses coffee, and if the first person chooses tea, that's a different selection for the 7 people. But for the people um, in the room service, they don't know who got what. They will look at these two and they will think that these two are the same. These two are the same selection because this selection here has 3 coffees. This selection here has also 3 coffees. So room service people will look at these two and they will think it's the same selection. So the question is how many different selections can the room service people actually see or receive? And so I listed here some of the different selections. For example, there could be 5 coffees, 1 milk, and 1 tea. Another selection would be 5 coffees and 2 milks and no teas. One interesting way of solving this problem is by modeling the problem with a tally diagram. And so you tally the 3 types of refreshments. And for example, one selection here that is listed here is 3 coffees, 2 teas, and 2 milks. And here's 5 coffees, 1 tea, and 1 milk. And then from that diagram, we convert each selection into a word. Yes, a 9-letter word. And the 9-letter word comes from the X's that you see here. Each selection has these X's. And the letter I that you see here comes from this vertical line from the tally diagram. And this way we can express each selection with a 9-letter word. So here it's X, 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 and then we put I here in the letter. And then X, X, here's another line, and then X, X. Here's another selection. This would be 5 X's. Here are 5 X's, and then here is the vertical line here, the division there. That's the letter I. This one would be 5 X's and then II, because there's no X in here for T. And let's take a look at this. Now the problem is now modeled by uh, permutating or arrangements of letters of these words, or of the 9-letter word. And this 9-letter word will have only X's and I's. And now it's just a matter of figuring out how many arrangements you have. If you have 9 letters, and there are only 2 groups of letters. In this case, there is 1, 2, 3, 4, 5, 6, 7 X's. So 7 X's and then 2 I's. And here, again, there's 7 X's and 2 I's. So each selection is associated with this permutation of the letters of the word XXXI, XXI, XX. That's an interesting way of modeling the problem. This comes from permutation. It's interesting to see this relation between selection, combination, and permutation. Now that 9-letter word will give us 9 factorial, and we divide it by 7 factorial because there are 7 X's. So 7 of those letters are repeated, and 2 of those letters are also repeated. That gives us a total of 36. Another way of doing that is using combinations. Again, this comes from theorem 8.7. Out of those 9 letters, or 9 slots for the letters, you're selecting 7 of those slots for the X's. And then the remaining slots, which is only 2, you're picking 2 of those 2 slots for your I's, for the letter I's. So that gives also the same answer. Now there is a theorem that gives us the formula for the number of selections when elements can be repeated. Again, it's much easier to recall the tally diagram and calculate the number of selections that way than to memorize the formula from the theorem. Theorem 8.8 gives you the formula. If repetition is allowed, the number of selections of S elements that can be made from a set containing T distinct elements is given by this formula. So in the previous example, S here is the 7 people. T is the number of types, number of drinks, coffee, milk, and tea. So we plug that into the formula, and that will give us the number of selections.